So, today is again one of my fun lectures. It's looking at microkernel design and implementation. So, what's really behind the way SeL4 is built, and sort of give you a bit of an idea of how we got to where we are and what we learned basically over a period of 20 years. So, L4 microkernels have been around for a while. And SeL4 is not the first one to go into products. That happened since the late 90s, I think. Most of these things here are deployments not of SeL4, but of other L4 versions, including some commercial clones. Although the military trucks and the autonomous helicopters, these are SeL4 systems. The iPhones, they have one of our older L4 kernels running on their secure enclave, and the others are different systems. So, it's been around for a while, it's been used for a while, so how did we get here? So I'm going to talk about how L4 came about in the first place, and then sort of look at some of the design and implementation issues, and really what did we learn and how that influenced SeL4, and then sort of step back and see what we really learned over the years. So microkernels sort of started in the 70s. There was one system called the Nucleus from Brink Hansen in Denmark, and that sort of got largely forgotten, but it had all the right ideas there. So reading that paper is actually very instructive, because it's even though the language is different, because computer science language already sort of got standardized in about the 70s or so, the basic concepts are actually all there and fairly clear. So that was the initial one, and then in the 80s the idea had a revival, and everyone was building microkernels, and then in the 90s the big sort of setback came, because, and that's sort of summarized here, so the most well-known microkernel of the day, and actually that was the system where they coined the term microkernel, was Mach from CMU, Carnegie Mellon in the US. And it was representative for these, what we now call first-generation microkernels. And unfortunately, it was also representative in terms of performance. So it had an IPC cost of the order of 100 microseconds. Now, if you think about if your IPC costs 100 microseconds, you can't do many of them until you hit into serious performance overhead. So if the average amount of work you do in an invocation is, say, a millisecond, and that's a fair amount of work, right? You should be able to do a lot of it in a millisecond. Then doing 2 IPCs there and back is a 20% overhead, so that's pretty substantial. And if the invocation are more fine-grained, then the overheads really flow out. And this is what people experienced, and it actually led to the point where IBM had a very ambitious project that really tried to make the best out of the microkernel idea of having just a kernel underneath and then multiple operating systems, personalities on top. They were selling 3 or 4 operating systems at the time, and they had this idea, okay, well, this is a cool thing, we can sort of simplify our product line by basically having them all personalities of the same microkernel that deals with the hardware. And that project was canned in '95, I think, and by that time had absorbed $2 billion, 1995 US dollars. That was a huge amount, so that was a pretty big disaster. And after that, microkernels had a really bad name. For a long time, we couldn't publish a paper that had microkernel at the title abstract, because people were so averse to it. And the core thing is here, right? The poor performance of IPC, which then translates in overall poor system performance. But the same diagram here, and I've stolen that from one of Jochen Liebke's papers, is that there's a huge gap between the inherent cost and what the microkernel actually delivers. So the steep line there is the cost of the IPC cost in Mach depend on the length of the message. And the green line underneath is the pure copy on the same hardware. And you see not only is there a significant gap, but the slope is dramatically steeper in the mask system. So even though you think, well, a message passing operation has sort of a constant overhead plus a overhead proportional to the message length, well, you see the proportionality is there, but it's the wrong slope, because there's no inherent reason why the slope should be steeper than the green line, because it's really then just a copy. So something is inherently wrong there. And this is then L4 came on the scene, and the dark green line is the same for L4. And you see it starts off being a factor of 20 fast to start with, and the slope is at least close to the slope of the basic hardware copy. It has this funny kink there. Why would that happen?
Caches.
Okay?
Caches. Memory hierarchy.
Explain.
Well, you pass in certain limits. There's certain. I'm guessing L4 uses a certain strategy for one for a certain region of lengths, and for anything longer than that, use a different strategy.
It doesn't actually use, it's the same code, but you're basically right. This is the size of the L1 cache, right? Once the message overflows the L1 cache, you have cache misses, and then the performance drops. But you see, it's at least sort of close to the hardware limit, right? And that's basically what we would hope to see. And so, where does this huge difference come from? And it turns out it is actually the cache. So Liedtke in his 95 paper, which we just read in the TS reading group yesterday, actually basically showed that using the data the Mach people had collected and published themselves, by just interpreting the data they had published, he could show that this overhead is mostly cache misses. And he could also show it's basically capacity misses. So the footprint of the Mach kernel is just too big. And so you need to think back, early 90s, systems just had one level of cache, and it wasn't particularly big. And so the sensitivity of the system to the effective cache utilization is pretty significant, pretty strong. So the takeaway for L4 from this was, well, we have to keep the system really lean. We have to make sure that we keep our cache footprint small, and then we have a hope on to actually get decent performance. And that's easier said than done. It's just not just looking at the implementation of IPC. It sort of really comes back to the whole system design. And really it comes back to minimality. So the idea of minimality was actually in the very first, what I would call microkernel these days, so in the mid-70s. But Jochen really, in his attempt to improve his previous L3 system to come up with L4, really explicitly stating it as the driving force for the design of the system. So it says that if a feature does not have to be in the kernel to achieve the required functionality, then it should not be. So really very strict minimality. Only code that has to be in the kernel should be in the kernel. So anything that obviously massages privileged hardware state like page tables, etc., that needs to be in the kernel, because that's the core mechanism for implementing any security in the system. But things like device drivers, there's no reason device drivers have to be in the kernel. And so L4 was not the first system that had device drivers at user level, but it made it one of its core principles. And so this is what happened since. So in the early 90s, there was this transition from this earlier system L3 into L4, what became then L4, and that was sort of stabilized by about 95. And then that was for Intel 486, later Pentium, and we here did the first 64-bit implementations on the MIPS. That was actually Kevin on his PhD that wrote the first MIPS kernel. And that became the first platform for advanced OS teaching. It was a MIPS board running our then version of L4. The original L4 was already in assembler. The MIPS version was part about a third or half in assembler and the rest of C, so anything that's not so performance critical was in C. And then there was this hazelnut kernel, which was a transition thing that was the first one implemented in C completely. And then Fiasco was built in place, and that was in C++, and continues to be a C++ system like this Nova hypervisor that got built from scratch later. And then Jochen's students, after he passed away, built the Pistachio kernel, which was also implemented in C++, and we then took that on, built a version that was aimed at embedded systems, and that got deployed in the first sort of really large-scale deployments on Qualcomm chips and later on iPhones. And then we did, in about 30 years ago, we finished the first version of SeL4. And so that's basically the historical context here. So to be a bit more specific on what was driving this evolution of these multiple kernels was really looking at what had worked and what had not worked well. So in particular, these first generation kernels, Mark was one of them. There were a large number of them at the time. Some of them still around. QNX is still used. It's strong sort of in transport system or the automotive industry, etc. uses QNX a lot. Chorus was, QNX was actually the first commercial microkernel. Chorus was a system that was around for a long time, I think from India. They all were sort of similar in many ways, and the similarity was that they actually were nowhere minimal. So if you compare this to the minimality principle of, well, the kernel contains scheduling memory, okay, device drivers, swapping, file systems, like that is really not minimal, right? So they had in common that they had too much functionality in the kernel, and therefore the kernel was too big, and therefore that translated into bad performance. Among others, the original Mach version 3, which is sort of late 80s, early 90s, had 180 system calls. Like, honestly, this is more than the original Unix had. 100,000 lines of code, and as I said, 100 microsecond IPC. That was not just Mach, that was sort of representative of those systems. And then Jochen basically stepped back, analyzed what the problem was, and came up with this new L4 design, which is then was considered a second generation microkernel. So taking the minimality really seriously. Minix 3 happened at about the same time. Pipewise was a commercial clone, originally called P4, of the then L4 version. Green Hills Integrity is a also commercial system from Green Hills that's used in aerospace a lot. Has a degree of verification story, but in sort of conceptually very similar to an L4 microkernel, even though it has nothing, no code or IPA inheritance or anything. And sort of what characterized the second generation kernel is that they became much more minimal. Jochen never claimed that he had an actual truly minimal microkernel, but he had a good approximation. So in particular, all the stuff which we now know shouldn't be in the kernel, he took out, and that was really the first, he was really the first one to do that, in particular, being really systematic about no device drivers, and really nothing that should be done in user level. It reduced the complexity in many ways, right? So one of the things he did was really thinking about, if you want to be minimal, what mechanisms do we really need? And dramatically reduce the number of abstractions exported by the kernel, and with that the number of system calls. Number of system calls went up and down. It was 10 at one stage and 7 at the other stage, but it sort of stabilized at about 7 system calls. 10,000 lines of code, so that's an order of magnitude reduction in kernel size, and he got an order of magnitude reduction in IPC cost. And this is different hardware, but I'll have a direct comparison with hardware later. well, we had it before on the previous slide, right? 100 or 105, I think, against 10 microseconds on the same hardware. No, 5 microseconds. The difference between L4 and both Minix and integrity is actually performance. Like, the Minix and integrity are both at least a factor of 10 slower than SeL4 than the L4 was in terms of IPC performance. So they weren't really faster than the first generation. And then SeL4 is considered the third generation, 13 years old now, and we went even more radical and took memory management out of the kernel, and of course that's where you derive a lot of fun from. To the point where we really think it'd be too dangerous to let you loose on naked L4, and we give you a memory management library. So the advantage is it's even more simplified, number of syscalls reduced, or that was partially because it's a capability kernel, of course. The code size still the same, about 10,000 lines. Fast IPC, but that's just a hardware artifact, right? This is an improvement in hardware speeds. And the real innovation was that, we had, well, capabilities are not an innovation. Mark had capabilities in other systems before, but a really strict design for isolation. We'll have a look at that. And that included taking the memory management out of the kernel. So the drawback of SeL4, you have to come with your own memory management library. But it's sort of, it's true minimality, and it really drives isolation, because the way memory writes are delegated in SeL4 by retyping from untyped, this really allows you to have complete isolation of resources, not only at user level, but the user level isolation permeates into kernel memory. And that is what allows us to formally reason about isolation properties in SeL4, because we know that things are separate inside the kernel because they come from different user level memory pools. So this is sort of an interesting diagram because it compares different L4 implementations over the years. So starting with the original 486 kernel, the assembler kernel Jochen did in it's sort of a bit vague when L4 actually started, but it was around that time. Then the same on the Pentium, then the kernels we built on Mix and Alpha, which was originally started in place, and then we continued it, Pentium 4, Itanium, etc. And what you can say, the IPC costs in terms of cycles, they go up and down. And that's not really a reflection of implementation quality, it's more a reflection of hardware. So hardware for a while, initially hardware was reasonably context switch friendly, and then it got really bad, and the worst processor I ever built was the Pentium 4, certainly in terms of microkernels, but in terms of many other aspects as well. It was just horrendously complex and pipelined and everything, and just trapping into the kernel would set you back, I don't know, 700 cycles or something like that, just to take the kernel trap. Really horrendous. Was the successor thing that unfortunately Intel managed to completely destroy was the Itanium, which is just the opposite. It was the best, the most complex switch-friendly machine that's been built in the last 3 decades, and we could do an L4 IPC in 36 cycles. That's really impressive. One of the things that enable that is on the Itanium, you can enter the kernel without taking a trap. So it has this notion of guard pages which are have a special mapping attribute in the TOB or in the page table. And if you jump to one of these, you can change the execution mode. So that's an attribute of the mapping that if you jump there, you're in kernel mode. And that comes together with guarding the entry point. So you can only jump to specific entry points. And that's a predictable jump, and so you basically can enter the kernel in a single cycle. And there are other tricks there. And then the RISC architectures, you see that generally around sort of 100, 200, 300 cycle marks. And even Intel has improved recently in being more context switch friendly. RISC-V, the 500 cycles, that's not particularly well optimized. That's on a small relatively slow processor that can be done much better. And of course, if you look at that in terms of microkernel, microseconds, like the actual latencies, yeah, things have improved a lot, and again with up and downs depending on the hardware. But we're consistently fractions of a microsecond these days. But SeL4 is still sort of alone in this. This is a comparison done by completely arm's length researchers in China who were pushing their own bandwagon. They analyzed SeL4 and two other open source microkernels, so the Fiasco thing from Dresden and Zircon, which is a new Google microkernel. And if you look at the latencies here, basically Zircon is like a first generation microkernel. It's a factor of 10 slower than SeL4. And I really don't get why Google had to do their own. I think it says more about Google than anything else. They should have just taken SeL4. And turns out our own measurements show it actually a bit faster even. But what's really interesting is how much of that is inherent cost versus software overhead. And the colleagues from Shanghai Jiaotong actually did us the favor and analyzed that as well. And so this is what you can find in their paper is the cycles for on this hardware, just the syscall instruction. So this is entering the kernel, sets you back 82 cycles, getting out of the kernel. Is this really? I need to check that number. That seems too high. But basically, it's significant cost, and then switching. I think the two are swapped. Sorry about that. 75 is the. This comes from just putting new information to the slides, right? The 75 is the return from the kernel, and the 186 is the cost of switching page tables. Very expensive operation on the Intel architecture. So these three are things you have to do, right? You have to trap in the kernel, you have to get out of the kernel, you have to switch page tables. That's inherent in the cost at rest-based IPC, and that alone on that hardware is 343 cycles. So this is one way. So going round trip, and the other table is round trip numbers, you see 686, that accounts for almost all the cost here. So what we can see is the costs in SeL4 IPC are dominated by the hardware costs you cannot get around. You have to, you just have to cop. Whereas the other kernels, they are far away from that. So their IPC latencies are dominated by software overhead. And so one of the takeaways is we may not be the fastest microkernel forever. I'm pretty convinced we are right now. But you can't improve a lot on it because we're so close to the hardware overhead, right? You may be able to shave 10 or 20% off at best, but you can't possibly be a factor of 2 faster than L4, SeL4, whereas SeL4 is a factor of 3 or 10 faster than the others. Okay, the other thing to look at is how has the kernel code size changed? And everyone knows this, right? Software grows over time, and certainly for my Macs, that's pretty obvious. If the system gets 3 years old, suddenly it's really slow because of software code mostly. I wouldn't say that's deliberate by Apple, but who knows? So if we compare that with the various L4 kernels, we see the origin one, 6.4 kilo lines of assembler, so 6,400 instructions. That probably maps onto something like 4,000 lines of C, 4,500, something of that order. So it was extremely tight. The others were larger. That was partially hardware complexities, particularly in the alpha. But generally, we stayed around the 10,000 lines of code size. The outliers are the Fiasco kernel, which is significantly bigger, supports too many APIs, and our L4 embedded kernel on the other side, but that was not reduced functionality, so that's not a complete general purpose kernel, unlike the others here. And then, yeah, we're back to about 10,000, give or take. It does depend on the architecture. So, quite in contrast to normal development of systems, we managed to really stay small despite learning a lot and adding new functionality. So SeL4 definitely has functionality that wasn't available in the earlier kernels, so to address usage domains that weren't really well supported. Okay, so this, yep.
Do you know how many lines of code Zircon is? The Fuchsia kernel?
Yeah. No, but it shouldn't be hard to find out.
I looked up a bit.
Let me say, I bet you $100 to 10 that it's multiple integer factors bigger than SeL4, most likely more an order of magnitude. Okay, so this is how the L4 microkernel kernel family evolved or developed. So why did we have to do a new one in SeL4? Any ideas? Turns out that's not an easy question to answer. There's multiple factors here. One of them is we did want to verify it, and we experimented with verifying existing code and came to the conclusion code that's not written for verification is impractical to verify. That's way too expensive. So that alone was a good reason. But we also knew that there were issues with the existing L4 kernel design. And so this is basically what we learned in the 10 or so years leading up to SeL4. What the second generation kernels, in particular L4, did was solve the performance problem. So L4, the original version, was just blindingly fast, and as I said, the later ones sort of were still in the same ballpark, and generally very close to the hardware limit. But there were a number of issues that were not resolved. And here's a probably not completely complete list, but certainly all the major ones. So one is that it had a global thread namespace. IPC was addressed to thread IDs, and that required thread IDs being a global namespace. And as John Shapiro pointed out 20 years ago, that is actually gives you covert storage channels, because you can, by signaling whether a thread was present or not, or by making a thread, certain thread ID present or not, you could signal to an attacker who could probe the namespace, basically. So that's a bad idea. The other thing is there's actually implications from that. And it is if you want to have a multi-threaded server, say, then because IPC is addressed to thread IDs, you have to send your request to a particular thread inside that server. Now, if the server is multi-threaded, then either you have to expose this thread, the internal structure of the server as its multiple threads, to the client, or you have to have an indirection where there's a gatekeeper thread that receives requests and then forwards them on to worker threads. And of course, the first one is poor information hiding and basically restricts you on playing with the implementation. Whereas the second one, of course, introduces overhead, because the message that came in has to be handed on typically via an internal IPC and then back, so you basically double your IPCs. So that's not so great. And the other is that it didn't have a proper authority delegation. It had an idea of hierarchical address space, process hierarchy to have a degree of resource control, but hierarchies are always restrictive, right? They get in the way. And the way this was done had significant performance implications. So all these three issues are very elegantly solved with capabilities. And that's what we did. So turning, really learning from this experience. Vika intentionally did not use capabilities. It had been used in Mark before, because he could shave a few cycles of the IPC path, and he was extremely an extreme optimizer. But in hindsight, that was a mistake. And really the additional cost of capability is literally a couple of cycles also on the IPC part. And it really solves a lot of these problems because capabilities have a clear delegation model, you can revoke them, etc. So that's a big improvement. And that's certainly the one defining characteristic of third generation microkernels. The other was this thing that the kernel had this memory pool, which of course opens it up to denial of service attacks, right? If you create a new address space, or if you just keep on mapping pages in your address space, then of course that consumes kernel memory, because for every, say if you have a large address space, you just map stuff sparsely, then you can force the kernel to allocate a new page table for every mapping basically. And that sort of, that way you can force the kernel to basically run out of memory and then deny service from others. So that's obviously bad. How did we solve that in SeL4?
Kernel doesn't manage memory.
Exactly, by making it the user's problem, basically. So, yeah, the SeL4 memory management model. And the third one, and I'll go through that in a bit detail, is the unprincipled management of time, which the original SeL4 didn't solve. We basically left time as a to-do later and finally managed to end up fixing that a few years ago. And this is what characterizes your MCS kernel, that it has capabilities for time, basically, and therefore a principled time management. So this one was really left out in SeL4, and we fixed it now. Of course, the MCS kernel is still not verified, so it's still not mainline because of that, or not the default kernel. But the verification is in progress, and hopefully next time around I can actually say that's the SeL4 kernel. Sort of frustrating a lot of this stuff. Okay, so these are the basic issues that are addressed by SeL4 at the design level. But then there is also interesting implementation aspects. Most of them, or some of them, are common to L4 kernels, and some are sort of really specific to SeL4. So the one is the fast part, the IPC fast part. Of course, the original L4 didn't have an IPC fast part. They didn't have any fast part because everything was fast part, basically. Everything was really micro-optimized to the last byte. The later generations, particularly the ones written in C or C++, they had then this notion of the fast path to optimize the most common operation that really needed to be fast. And this is on an abstract level how the fast path for the send path of a call IPC works in SeL4. So you start with the receiver blocked on the endpoint and the sender executing and trapping into the kernel. And then you get, okay, some prologue, which has to happen on any system call. Obviously, you have to do some minimal state saving, particularly when you expect a context switch. You need to save the processor state, etc. And then find out, okay, what are we actually doing? Find out, do a capability lookup to say, okay, what kind of operation is this? Is this an endpoint? And if so, check whether there is a receiver waiting in the endpoint queue. Remember, before the break, I talked about how endpoints are implemented. No, that was actually week one. How endpoints are implemented, and they basically queue either senders or receivers. And the normal expected case is the receiver is waiting on the endpoint, and then the sender finds, okay, there is at least one receiver queued, and then we can, that's one condition for doing a fast path IPC. If there's no receiver queued, then you have to manipulate queues, etc. So that's done. Check that the receiver is actually able to take this call legally, so it's still runnable, and that's important for fast path. Does it have a higher priority? Because if it doesn't, then why does the receiver's priority matter here? The whole point of this, checking this in the fast path, it allows you to do something quickly which you can't otherwise do. So what would that be?
Or if the receiver's priority is higher, then it's going to run anyway after we finish.
Exactly.
If it's not, it can't run anyway.
Yeah. So remember, we have a strict priority system. So by the fact that the sender is running to this point means its highest priority. Therefore, if this receiver that's blocked waiting to receive has a higher priority, we know that this is going to be the highest priority thread and we can switch to it without invoking the scheduler. However, if the receiver has a lower priority than us, we have no choice but invoke the scheduler to find out whether there's something else running, because the presently highest priority thread is getting blocked in the operation. Right? So we know we have highest priority, but we know we're going to block. We have no choice but run the scheduler. So this is an important fast path condition that allows us to switch to do the IPC without invoking the scheduler. And then we're almost done. We need to mark the sender as blocked, and in principle enqueue it into a waiting queue. In reality, this is just manipulating the reply object provided by the sender. It gets blocked on that reply object, and then we donate the scheduling context. I'll explain that later. And then we are done with everything we had to prepare, and now we need to do is the context switch, which is obviously switch the register context, and if there is the message exceeds the virtual register, the message registers that mapped on physical registers, then we need to do actual copying into the IPC buffer, so copying the virtual registers. If the message fits into the physical message registers, then there's nothing to do, because we just don't context switch them, and the data gets automatically delivered to the receiver. And that's it, and then we can return. And so this is a very tight code path, right? And on the ARM-E9, which is your Odroid, it executes in about 150 cycles, of which probably 100 or so are just a few hardware operations. Okay, so the scheduling context donation, this is the so-called direct context switch, which we'll get to later. Other fast path coding tricks that are also common to L4 kernels is to make the decision of the decision between hardware and between fast path and slow path as efficient as possible by just mapping everything on a single jump. So basically it collects the fast path conditions, so this is just a simplified version of that, force together various conditions that, if they are satisfied, will force the slow path. So one is that we're actually invoking an endpoint cap. If it's not an endpoint cap, then that's not a fast path operation, or there's a few others, but mostly they're endpoints. And if the capability on that endpoint doesn't actually have the send byte, then obviously we're back into a slow path. That's an exception, etc. And then, so these get added together, and then there's just a single conditional jump. If this value is non-zero, then jump away. And the fact that it jumps on non-zero is also intentional, because that helps the branch predictor. The default in the branch predictor is to predict the branch is not taken. So collects the common cases in a way that allows us to do a branch of 0, and for the slow part, and then just continue straight line in the fast part. So reduces the branch predictor footprint and actually operates already with a cold branch predictor. The branch predictor is basically a cache of branches taken from this instruction. and avoids misprediction, etc. And obviously is also cache friendly because all the fast part code just immediately follows after that, so it's in as few cache lines, instruction cache lines as possible. Because it does some redundant checks, which then the slow path does again, it actually penalizes the slow path slightly, but that's just order of 10 instructions. There's one fast path, slow path where it may be 20 instructions or so. But compared to the typical slow path cost, that's pretty irrelevant. So it's obviously a win only when we mostly take the fast path, but that's typically the case. That's how we pick the operations for to be fast path, obviously. So this is standard techniques been around from the early days of L4 kernels. Some of these things are no longer as important, in particular optimizing for branch predictor, etc. These things have become so much better in the meantime. We probably would not make much effect to do it the other way around, but you still know that this is definitely not bad. Okay, so that's sort of established stuff, and now I'll have a look at the things that we're now doing different from early L4 versions. And one of those is that L4 was always sort of had the notion of it should be able to be real-time capable, but if you remember me saying in the real-time lecture, real-time is not real fast. Just being fast is not sufficient for real-time. What's a really critical thing for real-time?
Meeting deadlines.
Yeah, and what do you need for meeting deadlines?
A good scheduler.
Hmm?
A good scheduler or an appropriate scheduler.
Yeah, well, just fixed priorities is fine, as we saw. No, the critical thing is that you have a bounded worst-case execution time, right? So you can actually reason whether you can meet your deadlines. And that was an issue in the early L4 kernels. Now, one of the things that is actually characteristic for all L4 kernels, with one exception, and they quietly admitted defeat mealtime and change back, is that the kernel executes all with interrupts disabled. So the advantage of this one is you don't have interrupts enabled when you're in the kernel, so you know you can't be preempted, and that means you know you're single threaded, you don't need any concurrency control, at least on a single core. Now, if you have preemption inside the kernel, then you need lots of critical sections because you obviously manipulate shared data structures. Now, initially this was just done for average performance because it's obviously faster in average if you don't have to take locks, and it has a better average case performance. But it's also, obviously, concurrency is hard, we all know that, right? And whether you try to verify formally or just by standard testing and code inspection, etc., concurrency is hard and is error prone. And so it was done partially for performance, but also partially for simplifying the kernel to make sure it's actually right. And the question is, okay, this is fine as long as all your system calls are really short. But there are some long-running ones. Turns out in SeL4, there's actually only one long-running system call. Have you guessed what that is? It's not a really long-running system call. It suspends you, right? But the system call itself would be short. Well, just think about what are the operations the kernel does. You can invoke capabilities, and defend this on the kernel objects, right? You can create new capabilities by retyping or by minting. You can destroy capabilities, and that's about it. So which of these can be long running? Nope. Destroying a capability, because you have derived capabilities, and so there's a dependency tree there, and you have to clean that all up. But there's also other cases that are much more critical. So in SeL4, one of the really design criteria was to reduce the number of long-running system calls to bare minimum. original L4 had many more. But it still was non-preemptible, and so the question is, how do you achieve real-time capability? Well, original L4 didn't really. And systems that are designed for real-time, for example, QNX or Integrity, or the IGOS thing, the ones I mentioned earlier, they basically run with interrupts enabled in the kernel. And that means you lose all these advantages, and I would say for a microkernel that's just plain wrong. So, but that requires you have to find a way to address the issue of long-running system calls, given that as much as we tried, we couldn't get rid of them completely without basically compromising what we wanted to achieve with the kernel. And the core reason why I say this is the wrong thing is not the performance driver, because, okay, maybe 10 or 20% in average case performance, you might be willing to sacrifice that to be able to do proper real time, but the correctness argument, in particular in terms of formal verification, it's just too horrendously difficult. So, how do we address that one in SeL4? And the approach taken there is what we call incremental consistency. So the idea is the kernel stepwise goes from one consistent state to the next. And the implementations are quite substantial. So this is sort of a rough, a very high level view of the kernel code path. You get kernel entry, and at kernel entry the hardware disables interrupts, and other kernels would then save state and then re-enable interrupts. We leave them disabled until we do a kernel exit, and then the hardware automatically re-enables interrupts. And that's all fine as long as we have short-running constant time, or at least bounded by constant time operations. If we have a long-running operation that's not bounded or not by any sort of halfway reasonable bounds, then the idea is we break this down into individual bounded operation O(1) operations, and ensure that the kernel is in a consistent state afterwards where the operation can be just restarted. So the idea is you perform something. So just imagine this is processing a queue. For example, your waiting queue on IPC. You take the first thing off, process it, and then you have a shortened queue, and presumably the kernel is back in a consistent state. And this is a point where you could just restart the operation. And that's what we do. So at this point, we check, is there any interrupt pending? And if so, we just exit the kernel in a way that will just basically return, keep the fault address the same, so the system call will just happen again. But in the meantime, we leave kernel mode, interrupts gets disabled by the hardware, and then if there was an interrupt pending, which presumably was, because that's why we do the exit here, then the hardware will invoke the interrupt handler that can do its job, and then we restart the system call, and then we have half of the operation already done and just continue. And so we have a guaranteed progress, but limited time of having interrupts disabled, and therefore can bound our interrupt latencies. And that's really the core to doing real time in SeL4. So that's the core property is here at the time where we check for pending interrupts. We are in a consistent and restartable kernel state, so we can just back out. And the advantage is, yes, our kernel is still concurrency free. Turns out this is a natural match for an event kernel here. Any questions up to this point? So here are the examples of implementing this incremental consistency. So the example I already mentioned is clean up an endpoint. So assume we have this endpoint, and there is, in this case, receivers blocked on the endpoint, and then we revoke the endpoint capability. And of course, that means we have to clean up this pending list because the IPC needs to be terminated for all the pending receivers. So obviously, the first step is to disable the capability, which means advantage of that one is, you know, from then on the list cannot grow anymore. Because the capability is gone, so it's no longer possible for another thread to get into the queue. And then we can clean it up incrementally, right? We have a loop, which we go through the queue of pending threads, takes one off, enqueues the next one, and then we have a valid queue. The kernel is back in a consistent state, but we made forward progress because we removed one, and because no new ones can arrive, we know this will terminate. So we have a defined upper bound for the overall operation, and every single step has a bounded worst case execution time. So this is a fairly straightforward case. It becomes a bit more tricky if we do something that affects only some of the queue threads. So if we have a batch endpoint, or an endpoint with batch capabilities, and we just revoke a particular batch. So in this case, we have potentially senders queued on the endpoint, and I misspoke before, it's of course the senders that are queued. Senders with different batches queued, and that's of course how you use batches, right? The server has hands out batch capabilities, send capabilities on the endpoint, so it can use the batch to distinguish state held on behalf of the clients. And if it now, say one client misbehaves, it wants to revoke that particular batch, so it needs to remove any thread in this queue that has the batch that is being removed. And this is a trickier problem because the queue can still grow. We know that once we invalidate that particular batch capability, no more orange threads can get queued in the queue, but further threads can get queued. So that means it's obviously a solvable problem. Every one of you could write the code to do that, but it's obviously more tricky because we have to keep much more state. And the complication here is that, remember, SeL4 has no heap. It can only use memory you have provided to it. And that means that state needs to be saved in the endpoint, in the capability, because there's no other place to put it. And that was the tricky implementation issue here, in being able to maintain that state without requiring extra storage. So the process here, if we want to remove the orange batch, we first, obviously, we go through the, in principle, the same process, but we need to keep more state because the queue can keep growing in the meantime, but not with things we have to deal with. So anything that can get added in the meantime, we don't need to worry about. So we just need to keep a pointer to where the queue was when we started the operation. So the state we need to keep is obviously the batch being removed. Well, we have that in the cap. The point at which we have progress, so when we restart the operation, we don't have to search through the whole list again, but we can start from the point where we left off, and wherever the queue ended at the time when the original revocation operation was started, so we know when we are done, even if more locked threads have arrived in the meantime. And that sort of complexity with sort of mangling that all into the capability and etc. is what really, and the revoking thread needs to be kept as well. That's what sort of scares the verifier. So you can see it doesn't really take a lot of complexity to make verification much more difficult. And that's the reason why this operation still hasn't made it into mainline. So if you want to have proper bounded operations, then you need to unfortunately still use a non-verified kernel. Or the alternative is, the problem goes away, of course, if you make sure that no more than one thread can hold a batch capability, in which case you don't have a problem, right? Once you found a locked thread, then you're done. Or otherwise just limit the number of threads that can ever be blocked on the endpoint. So you can do it, but it requires more complex system design. And then that gets us to optimization tricks. So this sort of incremental consistency is a new pattern in SeL4 compared to earlier kernels. lazy scheduling, that has been around from the beginning. And this is the idea that, okay, when you do, what a microkernels-based system mostly does is just invoking servers and returning. So you have a lot of IPC operations that are of relatively short duration, or the invocation of the servers of relatively short duration, and things change between being blocked and unblocked frequently. So in particular, originally the server is blocked, and then the client does a call operation that blocks the client, unblocks the server, and then the server does something, and then the server blocks again, and the client unblocks, and in terms of the server, we are more or less in the same state as before. It may have changed some of its internal state, but in terms of what the kernel is concerned, the server is back to where it was. And all the queues that the kernel maintains are back in the same state before the original IPC happened. And of course, if the server gets invoked a lot very frequently, then you have a lot of these queuing operations which you then undo shortly after. So the question is, okay, can we just simplify that? And the idea is, okay, well, because we are going to, when this server blocks, we're going to unblock it, or the client blocks, when we're going to unblock it pretty soon, just leave it in this block queue anyway, and then we clean up later. And so the idea is then the cleanup happens when the scheduler runs. So when the scheduler runs, it goes through the scheduling queue by priority, and at each priority, if there's anything queued, checks whether are these threads actually runnable, and if not, then okay, they're in the wrong queue, and we need to put them back into the queue, etc., or actually take them out of the run queue, and keep on going. That's all fine. What could possibly go wrong? Think real time again.
Running operation.
Hmm?
This operation could be very long running.
Indeed, it could. What bounds the operation?
Number of threads in the queue.
Number of threads in the system. Theoretically, each of them could be blocked, right? So it's bounded, but it's a bound you really don't like if you want to do real time. So in terms of real time, this is a really bad approach. And this has been sort of one of the original L4 implementation tricks. And in SeL4, we got serious about doing real time, so that was not acceptable. So how do you fix that without basically getting back to doing all these expensive queue manipulations, which you undo right after?
You'd have a bound on the time before the scheduler cleans up. So somehow ensure that you don't get too many unrunnable threads in the queue.
Yeah, okay, but say your time slice is a millisecond, that could still be a lot. So, well, there's actually a simple fix for this. So what's the, if you think about invariance on these queues, what is the invariant here that gets maintained and the one that doesn't get maintained? So naively, if I have a strict implementation, then the ready queue contains only runnable threads, and the blocked queues, like the endpoint queues, etc., contain only blocked threads, right? So in a strict system, these would be the two invariants. In this case, the invariant you violate are the ready queue only contains runnable threads. And we can easily solve this problem by basically reversing the violation. So instead of violating the invariant that the ready queue contains only runnable threads, well, this violates that. So we maintain the invariant that the ready queue only contains runnable threads, but we don't maintain the opposite invariant, which means all runnable threads are in the ready queue. And this is what gets you Benno scheduling. I call that after my former student who came up with this implementation. And the idea is, rather than being lazy on dequeuing from the ready queue, we're lazy in enqueuing into the ready queue. Why does that solve the problem? So now you have the situation that not all runnable threads may be in the ready queue, right? Because everything in the ready queue is runnable, but there's something that's runnable but not in the ready queue. How many of these could you have? So remember, this, it starts off with the client being runnable, assume it's in the ready queue, right? And then we block the client. We just don't manipulate the ready queue. And then the server comes back to the client, and then it's back in the ready queue. In the meantime, the server has been unblocked, but we don't enter it into the ready queue. And if now the scheduler gets invoked, if the scheduler only gets invoked when we're back in the client, then all is correct, right? The ready queue is still good. If the scheduler gets invoked, this time slice runs out while we're in the server, then the server was executing, but it wasn't in the ready queue. Turns out, well, if you think about it, that's the only case where this invariant is violated. The currently running thread may violate it, so it may be running even though it's not in the ready queue. So that's a simple fix, right? Because it's only the presently runnable thread that can be violating the invariant. All they need to do is, when the time slice happens, is that thread in the ready queue, if not, put it in there. So that's an O1 fix-up that is very cheap and only has to be done on when the scheduler executes. So basically, we get the same performance advantage as the original lazy scheduling, but we no longer have the problem with real-time with the boundedness of the operation. So this is a clear way. Turns out there's a case where it's not quite so obvious, and that probably was the reason why it wasn't done in the beginning. But that's how we do scheduling in SeL4 now. So this is one of the learnings in terms of implementation we got from earlier systems. So the other thing that was part of making IPC fast is what's called direct process switch. So this is the idea, okay, you try to avoid invoking the scheduler on the context switch, and I showed you that when we went through this fast part, how we check the priorities and not switch context, not invoke the scheduler if we know we don't have to, because we know that the target is going to run. And originally L4 basically did this, was always lazy in this respect. So it always did this direct context switch where basically you keep the receiver running on the sender's time slice. Is that what it really means, right? You immediately switch to the receiver without invoking the scheduler. The receiver effectively, temporarily inherits the priority of the sender. That's what it really comes down to, right? If the receiver is higher priority, then it's good anyway. If the receiver is lower priority, we just let it run on the sender's time slice and effectively giving it its priority. But it's very unprincipled, because this works all fine and makes sense if there's no preemption happening while executing in the server. If we invoke a server, then it sort of makes sense to let the server run on this client's time slice, because it's an action that was requested by the client, so it makes sense for the client's time to be paying for it. But a preemption could happen at any stage, in which case then the scheduler gets invoked and we execute on the server's time slice. So the whole server operation may or may not run completely on the sender's time slice. And an implication of that one is, of course, time accounting is really only extremely approximate. And that again is bad for real time, because for real time you need to be able to reason about whether your budget is enough to meet your deadline, etc. And if you don't really account for time properly, you can't really do that. So again, this is something that was useful for fixing up IPC, making it really fast, but it really meant there was issues doing real time on the kernel. The original fix was then, okay, at least do it only if we go to a higher priority to make it at least priority observed properly, but that's still not the full problem. And the real thing to solve this one is by making time slice donation principled, and this is done with introduction of scheduling contexts. So remember, in real-time systems I talked about delegation, where you share state between real-time tasks by encapsulating critical sections into a server that basically operates the critical section. And so you send your client invokes the server, and then the server may or may not run out of time and then get its own time slice or not, so you have this totally inaccurate accounting. And in MCS, we do this properly by having proper accounting with basically introducing capabilities for time. So the classical scheduling approach that was used in all L4 kernels, if you have essentially two scheduling attributes. You have a priority and a time slice, and if you don't have a time slice, you can't run. And in SeL4, we replace the time slice, or the MCS version of SeL4, we replace the time slice by the scheduler capability, so the scheduler context capability. And there's a hyphen missing, because otherwise it would be ambiguous. And the idea is, yeah, your scheduling context is basically a generalization of the time slice that gives it the right properties for properly reasoning about time. A scheduling context object encapsulates a number of attributes, but the main important ones are the period and the budget. And we've seen that before, right? Your budget can be up to the period, and the system guarantees that in any period you cannot consume more time than the budget. And that's sort of one advantage, is it allows us to limit CPU bandwidth, but also by handing around these scheduling contexts, we make time slice donation principled, and that's the real advantage of it. So, and I've shown that before, right? You can have multiple slices of CPU, and that allows you to reason about how much bandwidth you use, and you can reason that, okay, the system with those two threads is fully schedulable, those threads get there, are allowed to use their budget, and will never run out of it if their worst case execution time fits in the budget. But the real advantage is it makes this time slice donation principle. So this is when we use the passive servers, where a server doesn't have its own scheduling context, so it's forced to run on the client scheduling context. So a client invoking that server is forced to hand over its scheduling context for the duration of the execution of the server, and the server's time then gets basically billed to the client. And if there's a timeout now happening inside the server, this may or may not be bad, but it doesn't change the fact that the timekeeping is actually accurate, because the server, if it runs out of budget while executing on the client's scheduling context, well, it gets blocked until the refresh time of the scheduling context, and then it continues, but it's still operating on the client's scheduling context. So the benefit we do is we have actually proper time accounting, and the previously highly approximate and unprincipled time slice donation is really on a sound basis here. And that was a work of my PhD student Anna 5 years ago already. She time sliced, well, 4 years since we published, but she basically had work done 5 years ago. And so that's really sort of the driving idea behind the MCS kernel, that it really enables real-time, accurate real-time. In particular, these clients could be of different criticality, etc. And So the question is, yeah, what are the features we need for mixed criticality systems? And they sort of highlighted that when we did the real-time lecture. You need temporary isolation to be able to force things to run within their declared worst-case execution time, and this is what our budgets give us. And, we need mechanisms for resource sharing, and this is exactly what our passive servers give us. So the question is, what now happens if we run out of scheduling, out of budget, while the server is executing? So imagine you have two clients. The one of lower criticality happens to be able to invoke the server and then run out of budget. And of course that means the server is now blocked until the client's budget gets refreshed, and that blocks out the highly critical thread, and that may be a bad thing. So how do we solve that? How do we solve that in a principled way?
Do we elevate the servers, or that context priority to be the same priority as the critically high, the high criticality process?
So while we do priority, form of priority inheritance, we actually do priority ceiling, but the system doesn't automatically do that, but it gives you the mechanisms to do it. So you can run the server at the ceiling priority, because the priority is a thread property, not a scheduling context property. So the server will automatically run at the ceiling priority if you configure it that way, and so you maintain the priority ceiling protocol. But that doesn't solve the issue of what happens when the client, and the client might be malicious, right? It might know what its budget is and just wait till just before expiry and then call the server and then block out the other critical thread. So we need a way to recover from that. And of course, what's the proper microkernel way of doing this? Take memory management.
Let the user deal with it?
Make it the user's problem, exactly. So, and the mechanism of making it the user's problem is a timeout exception. So we now have the option of registering a timeout handler for the server, and in which case, well, that's the mechanism, and you can build your policies on top. And these are some of the obvious policies you can implement, like providing a one-off emergency budget for the server to keep on finishing this operation, and presumably you would couple that with shutting down the misbehaving client or something like that. Cancel the operation, roll the server back. That's particularly easy if the server is stateless. If it's stateful, then that's a bit more work, but you basically need some sort of a transaction scheme then. And then couple that with, downgrading the priority of the client or something like that. And if you really want to implement priority inheritance, you can layer that on top. I think it's mostly a bad idea. Turns out this is unfinished business, because yes, theoretically it's a solution that allows you to solve the problem, but it's not really a good solution, because obviously this comes with significant overhead. If you take out the timeout exception and then have to roll back the server, etc., that's not such a totally cheap operation, and it would be really better to stop a server with a client with insufficient budget to invoke the server in the first place. And so that's what I've got an honor student, Mitch, you probably know. He's working on that one. That's his honors thesis, on sort of coming up with the right model. The idea is fairly obvious, right? You have a barrier budget, and you let the client only invoke the server if it's got enough budget, and you can set this barrier. But the details, working out the details of the model to make sure it's right and has the nice properties you want, etc., is a bit more work. So this is what Mitch is working on. Okay, so that's sort of really a result of what we learned from L4 kernels in the past, particularly with respect to real time. But in terms of minimality, arguably the number one violation of the minimality principle, and in particular the context freeness of the kernel, is that we have a scheduling policy in the kernel, right? We have this fixed priority scheduling, and that's definitely a policy. And so to make the kernel completely policy free, it should really be part of user level. And there is a kernel called Composite, developed at Washington University, not George Washington University. There's a Washington University in St. Louis and a George Washington University in Washington, D.C. They build a microkernel specifically for real-time use, where they do all the scheduling at user level. So basically, whenever the kernel needs to be a scheduling policy, a scheduling decision, it does an upcall to a user level scheduler, and that does the decision and tells the kernel and goes back. It's a principal way, arguably. It's also significantly more expensive. How expensive depends how often you invoke the scheduler. If you have EDF scheduling, then that tends to be pretty frequent. So we decided not to go down that path and stick with fixed priority, basically with the argument that, well, you can build other things on top anyway. So even though we have a fixed scheduling policy in the kernel, we can still make scheduling decision at user level. And this is an example of implementing an EDF scheduler at user level with the existing L4 kernel. And Anna, as part of her PhD, actually did that. So the idea is you have clients that execute, they have their scheduling context, and they have a timeout endpoint, and the timeout server is the user level scheduler. So it basically sits there, waits for a client to run out of budget, and then it knows it needs to be invoked. And if it does that, then it determines who to run next, and allows it to get restarted. The clients all have full budgets, so whenever the timeout server replies, then the client is immediately runnable, and it makes sure that it only replies to one at a time, so that way it can control which of these clients it's in charge of is executing. So that's a straightforward way to implement an arbitrary scheduling policy at user level. And this is, Anna did an evaluation here, comparing it to a real-time version of Linux. This is the Litmus kernel. That's been done by Björn Brandenburg. And that's basically a test bed for all sorts of real-time work, and in particular it contains an EDF scheduler inside the kernel. And the green line is the cost of the scheduling operation in Litmus as a number of threads it's scheduling. And you can see it sort of interestingly gets faster with more threads for a bit for whatever reasons, and then it's sort of constant. And the red line is the user level scheduler implemented on MCS, and you see it's actually faster than the in-kernel scheduler in Linux. So performance seems to be fine. You could, of course, turn that argument around. Okay, it's obviously good. Why don't you use it all the time? Well, we want to be faster than that in most cases. And turns out fixed priority scheduling actually is has enough attractive properties that it's what people typically want to use. Okay. Questions?
Why does the user level scheduler have like a fixed budget? In the background, they don't have like a full budget.
Yeah, because it doesn't need more, right? It only needs enough budget to make a scheduling decision. And then it blocks again on waiting for the next timeout.
But you could have more budget.
You could have a full budget, yeah. Any other questions? Okay, so the second last topic I want to look at is comparing microkernels with hypervisors. So hypervisors are actually virtualizations are even older than microkernels. And if you listen to the virtualization lecture, I explain where they came from, etc. I'm not going to go through this again here. But they have sort of they've taken a similar development recently. So virtualization became sexy again in the late 90s, mostly driven by consolidation, cloud computing and all that stuff, right? And now everyone uses hypervisors. And they have some similar properties. And there's actually interesting similarities, much more than you would expect first off. So one, of course, is SeL4 is totally suitable to be used as a hypervisor, and we do that all the time. So that already shows you, well, that there is some commonality here. Right? So if you use SeL4 as a hypervisor, then it needs to know a little bit about more state, because virtual machines have more state than normal threads. They have additional hardware registers, so that's hardware imposed state, which the hypervisor needs to manage. And so that basically means, okay, there's some extra state to carry on context switches, save and restore. And on top of that, it needs to emulate virtualization events, right? If something happens that the hypervisor needs to act on, this needs to implement it to according whatever policy that hypervisor implements. Now, in SeL4, of course, it's a true microkernel. We solve this how?
Letting the user do it.
Making it the user's problem. In this case, the user is this user-level virtual memory manager, virtual machine manager. So that's just a component that does the actual virtualization work, and all we really need in the microkernel to support this is a new kind of exceptions that are virtualization exceptions that get forwarded to this user-level virtual memory manager. And then we're done. So it doesn't really take much to turn a microkernel into a hypervisor. And of course, the way we do this in SeL4 is that rather than having a big virtual machine monitor with a full Linux system in there, as SeN does, and a huge trusted computing base, we just have a virtual machine monitor that's associated with each virtual machine. So each virtual machine has its own copy of the VMM. And that was pioneered by the Nova guys in Dresden, and it's obviously the right model. Because that means we take the VMM, it's still in the trusted computing base of its virtual machine, but it's not in the trusted computing base of anything else. It cannot break isolation. So by having these per VM VMMs, they become untrusted, except for the VM itself, but the VM already trusts its guest operating system, which is this huge monolith of Linux. So trusting an extra 100,000 lines of code, who cares, as long as no one else needs to trust it. And that's a big thing, difference to something like SeN. So we keep the microkernel as general purpose. We just add this ability to reflect virtualization exceptions up to the user level VMM. And that's where the virtualization specific code lives. And this is the ARM view, where we have a separate hypervisor mode that's more privileged than the kernel mode. In x86, the model is different. We have an orthogonal mode called root versus non-root mode, and the hypervisor runs in ring 0 of root mode, whereas the guest runs in ring 0 of non-root mode. But again, we have a deprivileged virtual machine monitor which runs in ring 3 of root mode. So root mode, it needs root mode because it needs to access virtualization state, but it doesn't have more privilege than a normal user process. As a matter of fact, in this model, native SeL4 tasks would of course also run in ring 3 root mode next to the VMM. So that's the basic model of using SeL4 as a hypervisor. And so then the question is really, so what the hell is the difference between a hypervisor and a microkernel? And it turns out, well, they do a lot of the same thing, right? They execute obviously at the highest privilege level because they need to control resources in the system. And other than that, they abstract hardware resources. And they pretty much differ in the way they abstract hardware resources. The whole idea of a hypervisor, it has one-on-one mapping to hardware resources, right? Its abstractions are the actual hardware abstractions. Whereas a microkernel, as you've seen, has somewhat different abstractions, although in SeL4 we got way closer to the actual hardware abstractions than in earlier L4 kernels. Terminology had changed a bit. In the past, everything doing virtualization was called a hypervisor. These days, we distinguish between the hypervisor, that's a privileged thing, and the VMM that might be unprivileged. But in the end, it comes down, they have to abstract CPU, memory, I/O, and communication. And the difference between hypervisors and microkernels is really how they represent those abstractions. So if you look at what they are and how they are abstracted in the two different worlds, so looking at memory, traditional hypervisor will present control over memory by giving you a virtual TOB, basically. Now, a TOB is really a cache for page tables, so that's sort of really close to obviously close to the hardware. But of course, in SeL4, our abstractions for address spaces is really also page tables, right? We have pretty much a very hardware close version of page table abstraction in SeL4, and it's actually hardware or architecture specific. So we don't really try to abstract over the hardware at that point, and that's different to other microkernels. So the two are very similar at this level. If we look at CPU abstraction, in the hypervisor case, you have a notion of a virtual CPU. In SeL4, we call them threads. So they're really the same thing, right? There's something that represents CPU state enough that you can execute, and in particular it needs to be context switched. So it's a bunch of registers really. Communication, because hypervisors give you the illusion you run on naked hardware and everything else is a separate computer, the natural communication model in hypervisors is a network, because that's how computers communicate, right? You have a network, you have a device driver, and the network abstraction layered on top, and typically they actually run TCP/IP, which of course is crazy if you just want to communicate with a different virtual machine on the same processor. It's lots of overhead. And whereas in SeL4, or microkernels in general, we have a specific high performance communication paradigm that is optimized for communicating to different processes on the same hardware. So obviously this looks way more efficient than the other one, and in reality it is. And then I/O, well again, because in the hypervisor world, I/O is a device, and you have a device driver, you talk to it, and again in SeL4, that's well, as a user level device driver, all the kernel does is forward interrupts. So there's a much more significant difference there, and that is reflected in performance. So basically, there's similar abstractions, they're for the same things, but they're differently optimized. And as we see in the as far as the communication is concerned, the microkernel model, which doesn't try to represent communication as two separate machines talking to each other, is way more efficient. And so the left is sort of what we have in SeL, right? You have your hypervisor, which is operation, has the guest operating system, and has a virtual device driver, which basically converts the operating system device interface or driver interface into a communication interface that talks to the real driver. And that basically comes down to having something IPC-like, but hidden behind an abstraction that inherently imposes inefficiencies. And so the communication there tends to be much more expensive, and of course you have a huge trusted computing base because your whole Linux system is in your trusted computing base. So trying to use virtualization for security and then using SeN as the hypervisor is crazy, right? Hello, cubes. Because you have this huge trusted computing base. Makes no sense. But what it comes down to in I/O, communication between the device driver at least and the rest of the system is really critical. And in the microkernel case, this is done by highly optimized IPC, whereas in the classical hypervisor case, this is done by some sort of a virtual network abstraction and therefore less efficient. And it does tend to go into bottlenecks. When SeN first came out, as predicted that within a few years, and they ridiculed us L4 folks about being so paranoid about performance, etc. And I predicted, yeah, within 5 years you'll be writing papers about fast communication and hypervisors, and it didn't take that long because it's an obvious bottleneck. And of course, once you have your microkernel as a hypervisor, you can easily combine the two worlds, right? You can have stuff running in virtual machines and stuff running natively side by side. And that's a great way to enable legacy support. When you have a system that has limited functionality, you don't want to write all the world's new device drivers from scratch, etc. You can reuse stuff from, say, Linux by having a Linux system in a virtual machine. Obviously, you try to avoid that for something that is really security or safety critical, but for stuff that's not, that's a perfectly adequate way to do it. And if you do it right, performance is quite bearable. So it allows you to start with everything, the whole legacy stack in a virtual machine and then pull stuff out. It's called the incremental cycle retrofit, and we did that on real world systems, and I'm going to talk about that in the last week. Okay, so much about microkernels versus hypervisors. Any questions before I go up into wrap-up mode?
When you are using like the legacy system, it still uses a virtual network interface, right? Even on SeL4, right? So do you get any performance benefit or not? It's just like limited by
it definitely won't be faster than running the whole the native Linux system, right? You definitely pay. Yeah. But if some component, and really the only devices that are performance critical in most cases is network, gigabit network or 10 gigabit or whatever, and maybe USB services. And so, yeah, if that's a performance bottleneck, you can pull them out and run them native on SeL4.
Thank you.
Yes? Okay, so stepping back, what have we learned over the years? So the original L4 kernel that really defined the second generation of microkernels had what I classify as two major shortcomings. The one is resource control was really underdeveloped. And so we saw that in several ways. We saw that in terms of accounting for time. I didn't go into that, but I talked about the kernel memory pool, where you could mount denial of service attacks, etc. The need for having process hierarchies in order to restrict information flow in the system. They were not only inflexible, but they were also created performance issues, etc. So there's a number of things that weren't really well done. And the other thing is that with the benefit of hindsight, I must say the IPC abstraction was over-optimized. So Jochen mangled too much into the same abstraction. So in particular, it doubled for communication, synchronization, memory management, because establishing a mapping in address spaces, you send a page over IPC. And whereas in SeL4, you can of course grant the capability by sending it over IPC, but that's not the only way to establish mappings. In many cases, you can directly execute a map operation using a frame capability and an address space capability. And scheduling was also enabled in with time slice donation. So it was really an over-optimized abstraction, and that meant it didn't serve all purposes properly. And so when we did SeL4, from this, what we had learned over the previous 10 or so years, we stepped back, established a number of principles on how to design the kernel to basically get us over these limitations. And so the one was fully delegatable access control, and that's your favorite memory management system. Wasn't done properly for time initially. That's now done with scheduling context capabilities. So we now really have fully delegatable access control. All resource management subject use level policies, so that's really done properly in SeL4, including kernel resources itself. That's the memory management model again. We didn't compromise on performance, and that was really important for me. When we started the SeL4 project, and it was from the beginning, the idea was to build a kernel which we verify. I told the team that I will not consider this a success if we lose more than 10% in IPC performance compared to our fastest kernel before. And when we first published the first SeL4 paper, it was right at this 10% boundary. But within 2 years, one of my really awesome students improved their fast part and verified it, etc. And we are now faster than the fastest kernel we built before. Suitability for real time, so we really wanted to fix the issues we had with real time. As I said, it wasn't done completely in the first step, but finally done with the MCS model. And yeah, we wanted to formally verify it, and we knew that we couldn't do that on an existing code base, but it also required us to maintain a number of some discipline in the way the code is structured, etc. Turns out most of these restrictions we needed in order to enable verification was sort of well established in the in the L4 world anyway, including running with interrupts disabled, etc. And yes, interestingly, we weren't the first ones to try to verify an operating system. So this is a pretty famous paper, the so-called UCLA Unix security kernel, where they worked on verifying that one, and there's some famous names, in particular Kopek. And so they explicitly says, our research seeks to develop means by which an operating system can be shown to data secure, meaning that direct access to data must be possible only if the recorded protection policy permits it, blah, blah, blah. So basically security enforcement, right? Provable access control. And this was done in 1980. And in those days, the system they dealt with was too complex. So that's microkernels are really an enabler there. And the verification techniques were far away from being developed enough to make this tractable. So they didn't succeed. They managed to specify part of the functionality of the kernel, but not verify anything. And then 30 years later, we finally managed to do it.